All right, so let's go over the problems that you were looking at today in our Zoom class. We're going to start with this problem, which is very much an F equals MA problem, the kind that you probably did in Physics 1. So how I would start is, well, I'd read the problem. So we have this crate. It has a constant acceleration. Basically, they're giving us some information that will help us figure out that acceleration, the fact that it's going to start at rest and move 6 meters in 3 seconds. We'll get back to that later. We're also told that there's friction because we get the coefficient of friction, and we want to find the tension in the cable. So let's look at forces acting on this box. So we have the tension, and we have the weight, mg, we have normal force, and then we have the frictional force. This would allow us to write our sum of forces in the x direction will be m times ax, and the sum of the forces in the y direction will be 0. Just to remind us that the normal force acts along the y-axis, and the angle of incline is the same as the angle that the weight makes with the vertical. So if I look at forces in the y direction first, because I need the normal for friction, so I'm going to start with that first. I get normal is in the positive y direction. There's a y component of weight, which is given by mg cosine theta, and these equal to 0. So this tells me what the normal force is. Okay, so we're going to use that later. Here in the forces in the x direction of the tension, there's a component of weight that acts down the incline. So that's mg sine theta. That's right here, mgx. And there's also the friction, and that's equal to the mass times the acceleration. The acceleration and the tension are in the same direction. It accelerates up the incline, so they're both positive. All the other forces are down the incline, so they're negative. The frictional force is mu times the normal. And so one final substitution. And now I can rearrange this to solve for tension. The only thing I don't know is the acceleration, but I know that for constant acceleration, this is our expression for position as a function of time. If we let s not equal 0, and we are told it starts from rest, it's just s equals 1/2 at squared. We're told that it moves 6 meters in 3 seconds, so we have the information for s and for t. So we can rearrange to find the acceleration is 2 times s divided by t squared, which will be 2 times 6 divided by 9, which will be 1.33. So then if we go and plug in all our values, we have 20 times 9.8 times the sine of 30 plus 0.3, 29.8 cosine of 30 plus 20 times 1.33. There's all our numbers, and that gives us a tension in the rope of 175.5 newtons. And so that's that problem. That wasn't too bad. This problem I feel like is a little bit more reflective of what I feel like you should be learning in this chapter, because here we're told that the force acting up the incline is a function of time, and we'll see how that's going to work. We're told the initial velocity, and we're going to look at how we use that. And we're going to be asked to find velocity and position when t equals 2 seconds. So kind of like to use red for the forces. I'm going to just do that over. So the forces acting on this car are the force of the cable and the weight mg, and then the normal. We're not given any information about the friction, so we can assume that there isn't any friction acting on this. Because of the wheels rolling, we would only really have static friction, but that wouldn't affect, that actually allows the wheels to roll, doesn't really enter into our Newton's equations. So we can just stick with F equals ma, and so we have the 3200 t squared minus mg, and again this is theta and this is theta as well. So mg sine of theta equals m. I'm going to write this as dv dt because we're going to use it like that. Now, in this particular problem, they don't give you the angle, but they give you the triangle. And so let's use those ratios to express the sine of theta. It will be opposite over hypotenuse, which would be 8 over 17. And that equals to 400 dv dt. And so what I want to do is I want to solve this so I can write dv dt equals. So we're going to divide through by 400 all the way through. That's going to give me dv dt equals 8t squared minus 4.61. So that's the expression, and I'm going to integrate. I'm going to do a separation of variables, integrate both sides to get velocity as a function of time. So I'm going to integrate from time equals 0 to t, and then the corresponding limits on velocity would be its v naught. That's its velocity when t equals 0, which we're actually told is 2. I'm going to plug that in later. And then to the arbitrary velocity. So this gives me v, which I will evaluate at v naught and v. This will give me 8t cubed over 3 minus 4.61t, evaluated at 0 and t. So we get v minus v naught is equal to 8/3 t cubed minus 4.61t. V is equal to 8/3 t cubed minus 4.61t plus 2. That was the v naught. We're just bringing it over to this side. So we can evaluate at t equals 2 seconds, and we actually would get a velocity then, if you plug in your values, of 14.1 meters per second. So that's part of it. I'm going to go to the next page to do the position expression. So we had found that velocity was 8/3 t cubed minus 4.61 t plus 2. But we can also define velocity as ds dt. And this is how we'll get position as a function of time. Okay, so this will give me s minus s naught, and this will give me 8t to the 4th over 4 times 3 minus 4.61 t squared over 2 plus 2t. So if s naught is going to be 0, so we weren't told initial value, so it's fine to let it be 0. So 2/3 t to the 4th minus 4.61 over 2t squared plus 2t. And again, we can evaluate at t equals 2, and we'll get s is equal to 5.45 meters. All right, so let's go and look at this problem. This problem is where we're going to get into using different coordinate systems. I'm going to start off by labeling the forces acting on this ball. I get the tension in the rope, and I get the weight mg acting straight down. Now, as I read this question, one of the things they want me to find is the tension in the cord and then the increase in the speed of the ball. The increase in the speed of the ball, to me, reads acceleration, and specifically, to me, I'm thinking it's a tangential acceleration. And because of the fact that this ball is moving in a circular path, I'm thinking about centripetal acceleration, which is in the radial direction. And so I'm really compelled to use a coordinate system where one of the axes is along the radial direction and the other one is tangent to that because it's perpendicular to the radial direction, and it's also going to be along the direction that's tangent to the circular path. So I'm really thinking that I have a normal acceleration, which is v squared over rho, and I have a tangential acceleration, which is dv dt. It's the change in the speed. This means that when I'm looking at my forces, I have forces that are in the radial direction will be equal to mv squared over rho, and forces that are in the tangential direction will be equal to m dv dt. So when I'm looking at this, what are the forces along that radial direction? Well, and also keep in mind that this is directed towards the center. That's the direction of the centripetal acceleration. So I'm going to start off and make that the positive direction, and that would be my tension minus mg times the sine of 45. You know, this angle here is 45, this one's 45, so it's a little bit ambiguous which angle you're using and whether you use sine or cosine, and it ends up not mattering because of course they're the same. But these two are forces, what we're looking at. This is the radial component, the force in the normal direction, if you will, is given by mg sine of 45. That's outward, and that's why it's negative, and that's going to be equal to mb squared over rho. So that one is pretty straightforward. T is equal to mg sine of 45 plus mb squared over rho. V is equal to 3. Rho is really just the radius, which is 2 meters. And this becomes a plug and chug, where I got 114 newtons for the tension. In the tangential direction, you'll notice that the tension is totally in the radial or the normal direction. Only gravity has a component that's in the tangential direction. And so depending on which 45-degree angle I write it at, I would say that it would be mg cosine of 45 is the component of the force that is in the tangential direction. So that'd be right here. And that's equal to m dv dt. dv dt then can be written as g cosine of 45 degrees, which I found to be 6.93 meters per second squared. All right, so that's that problem. The last problem is just a little bit tricky because we have this curve that is, it's a parabola, so it's not a circle. So finding the radius is not as straightforward. We would want to find what we call the radius of curvature. So that was in one of our slides. We don't use it a ton. The definition for the radius of curvature is 1 dy dx, that derivative, and we square it. And this whole thing is raised to the 3/2, and then we divide by the second derivative of y with respect to x, and we take that absolute value. The y that we're using, of course, is y is equal to 20 times 1 minus x squared over 6,400. And so let's just find the radius of curvature first. I feel like it's going to take a bit of work, and so it might be helpful to know what that is. So dy dx is equal to minus 20 times 2 times x over 6,400. So that ends up to be minus x over 160 when we find common factors and get rid of them. D squared y dx squared is just taking the derivative again, which I'll get minus 1 over 160. Now when I use these expressions in my equation for radius of curvature, obviously you see that I need to use a value of x. And this 80 meters is my value for x. And so when I put it into my expression for the radius of curvature, I'm going to have 1 plus, and it's going to be 80 over 160. But I square that. It's raised to the 3/2. And then over the second derivative, which is minus 1 over 160, we're taking the absolute value of that. Because if you can see, we can't have a negative radius of curvature. And so altogether, I end up with a radius of curvature of 224 meters, which is going to be helpful later on. So we'll try to remember that. So let's go to another picture. So what we're asked to find is we want to find the normal force and the frictional force on the road by the car, which is going to be from Newton's third law, is the same as the frictional force that acts on the car. So I'm going to use axes. We're at point A. Even though the car's not there, that's where they want you to work. And I'm going to use, again, my radial and my tangential forces. And so I'm going to have my sum of my forces in my normal direction. It's going to be mv squared over rho. My sum of my forces in my tangential direction is going to be mass times the tangential. So in terms of forces, I'm going to have the normal force acting on the car. I'm going to have its gravity mg, and then its friction like that. All right, so in the normal direction, I have the normal force minus mg cosine of theta. Now, this is my angle theta, and right here, that would be theta as well. The sort of basically the angle of the incline at that location. And this is equal to minus mv squared over rho. This time, because the direction of the centripetal acceleration is towards the center of curvature, that's not in the direction of the normal force, and that's why they don't have the same sign. It's actually in towards the center, and so it has to have the same sign as the weight force because they're in the same direction. That's why we have the negative sign there. So let's talk about finding the angle, because that's another thing that's kind of tricky. If we think about right here where the car is located, it's supposed to be at point A, this angle is theta, and this could be expressed as dx, and this could be dy. So the tangent of theta can be written as dy over dx, which is just the derivative, which would be x over 160, which would be equal to 1/2. And so from that, I can figure out the angle is 26.6 degrees. Given that information, then we can find the normal force is going to be written as mg times the cosine of 26.6 degrees minus m. The velocity is 9, and we square that, and then my radius of curvature was 224. And so this is going to give me a normal force of 6,721 newtons. So we got that part. In the tangential direction, we have, so here they're talking about the acceleration. That's the acceleration that the car is experiencing, which would be tangential. So we have mg sine of theta minus the frictional force is equal to mass times acceleration. And this is where I can solve for friction. Normally we're used to doing mu and the normal force and all that, but we weren't given what mu was. We can just solve directly for the friction. So the friction force is mg sine of theta minus the mass times the tangential acceleration, which is equal to 3. And then we can find the frictional force is 1,110 newtons. And that is that problem. Hopefully you followed it. It's a lot of little tricks, but I'm not sure if you have something like that on your homework, but it's nice to know how you actually find that radius of curvature using an equation.